Well, welcome back everybody. I decided to start you off with an opener because I'm sure you have missed my openers. So I'd like you to find the limit as x approaches 0 of 2e to the x minus 2 all over x. Now, as I go through the lesson today, feel free to hit pause, try and work a problem out yourself instead of just watching me do it. Probably have a little more impact on you if you try it yourself first. Or just go through it, or don't even pay attention and try and do the homework and then get it wrong and then email me and waste all my time answering your questions. No, I'm just kidding. Alright, so how do we do this? Well, when we do limits, the first thing you need to do is try and plug in the value. But when we plug in the value, we get 2e to the 0. e to the 0 is 1, so we get 2 minus 2 over 0, which is 0 over 0, and that's no good. So the other things we've tried to do is, can we do any factoring and canceling, maybe multiply by a conjugate, or some other algebraic manipulation. And there doesn't seem to be any for this. So we have a problem when we wind up with 0 over 0, or maybe positive or negative infinity over infinity. And these are referred to as indeterminate forms. And a character from a long time ago named L'Hopital had looked at this and investigated this, and his thought was, well, even though it's 0 over 0 or infinity over infinity, maybe the rate at which they're going to 0, the numerator and denominator, or the rate at which they're going to infinity, matters, and if one's going at a faster rate or a slower rate, maybe we can figure out by comparing the rates. And obviously we know rates deals with our derivatives. So L'Hopital came up with this rule, and he said if we have two functions f and g and they're differentiable, which means they have derivatives, as x approaches a, if either both the functions approach 0, or they both approach positive or negative infinity, and if the limit of their derivatives exist, then it turns out that the limit of the original rational expression will be the same as the limit of the quotient of their derivatives. Now, the only thing that really sometimes students make a mistake at is when they're calculating the derivatives of f and g, you have to remember that f is a function which is in the numerator of the problem, and g is a function that's in the denominator. I'll show you what I mean in a second. So let's go back to the opener. So in this problem, the f is going to be 2e to the x minus 2, and the g is going to be x. So don't think of g as 1 over x if you're looking at the whole expression. Okay, and we don't want to make that mistake. So whatever is in the denominator, that's what the g function is. So to find this limit, it's going to be the same as if we find the limit as x approaches 0 of the derivative of the top, which is 2e to the x, and then minus 0, and the derivative of the bottom, which is 1. And now we can plug in 0 directly, and we're going to get 2 times e to the 0, which is 2, over 1. And if we went ahead and graphed the original function on our calculator, we'd see that as we approach 0, the limit is approaching 2. Alright, let's try another one. So people tend to get a little too excited about L'Hopital's rule, as some of you have seen earlier in the year. And when you look at this problem and you try and plug in 0, that's the first thing we always do. You get 1 over 0, that's no good. Minus 1 over 0, that's no good. Wait a minute. Isn't anything minus itself 0? No, I've been away too long. That's funny math. Can't do that. Alright, but the reason that we can't apply L'Hopital rule is because this is not in the form f over g. But if we can put it in that form, then we can apply L'Hopital's rule. And luckily enough, we know how to combine fractions by getting a common denominator. So I multiply the first fraction by e to the x minus 1 over e to the x minus 1. and the second fraction times x over x, and we have that. Now, if we try and plug in 0, we're going to get 1 minus 1 minus 0, that's no good, and we're going to get 0 times 0, and that's no good. So that didn't seem to help us. But why can't we just keep repeating L'Hopital's rule? So for this limit, that should equal the limit of the derivative of the top and the bottom. So in other words, f double prime over g double prime. So let's keep going. So we're going to do the limit as x approaches 0. And the derivative of the top is going to be e to the x minus 0 minus 1. And the derivative of the bottom, if I went ahead and multiplied that out, x e to the x minus x, I'm going to have to use the product rule for the first part. So derivative of x is 1 times e to the x plus x times the derivative of e to the x, and then minus x, so minus the derivative of x, which is 1. So now what happens when we plug in 0? We're going to get e to the 0, which is 1, minus 1. And then the denominator, we're going to get e to the 0, which is 1, plus 0, minus 1. That didn't seem to help. Well, when we're not sure what to do something. Let's try it one more time, which is, in essence, the third derivative of the original f and g. So, well, that should equal the limit as x approaches 0. And I'll be done with this, I think, before graduation. So the derivative of the top is e to the x. Derivative of the bottom is e to the x plus the product rule. So that's going to be 1 times e to the x plus x times the derivative of e to the x, and then the derivative of 1 is 0. Okay, let's see what happens now. Can I plug in 0 directly? In the numerator, I'm going to get e to the 0, which is 1. In the bottom, I get e to the 0, which is 1, plus 1, plus 0. Hey, wait a minute. That's 1/2. So, the derivative, the limit as x approaches 0, circle this in green, of 1 over x minus 1 over the quantity e to the x minus 1, according to L'Hopital, is 1/2. Now, not that you're second guessing me, but let's take a look. I happen to put this in my calculator, and let's hit zoom 6. And sure enough, if I hit trace, at 0 it's not defined, which we knew. It was an indeterminate form. And if I hit right arrow, if I get really close to 0, 0.48, how about if I trace at 0.1, 0.49, trace at 0.01, 0.499. So as I'm getting closer to 0 from the right, it's approaching 1/2. And if I go negative 0.1, 0.508, and how about negative 0.01? And sure enough, as we're approaching 0 from the left, it's also approaching 1/2 or 0.5. So, looks pretty good. Check. Alright, let's try a few more. What's the limit as x approaches infinity of natural log of x over x? So, with infinity, we can't plug in infinity, but if you think about it, the natural log of x is a graph that looks like this. It's increasing everywhere, or is increasing as we move to the right, and it gets higher and higher and higher, although not as quickly as something like y equal x. But they're both going to infinity, so L'Hopital's rule does apply here. And so therefore, that should equal the limit, as x approaches infinity, of the derivative of natural log of x over the derivative of x. And as x goes to infinity, 1 over x goes to 0, and 0 over 1 is 0. Well, that was easy. Okay, let's try another one. This is probably my favorite. So once again, limit as x goes to infinity, numerator and denominator are both going to infinity. So L'Hopital's rule applies. So let's take the limit as x approaches infinity. The derivative of the top is 1. Now, what's the derivative of the bottom? Let's write this over here on the side. Remember, that's x squared minus 1 to the 1/2 power. So the derivative of that is going to be 1/2 times x squared minus 1 to the negative 1/2, and then the chain rule times the derivative of the inside, which is x squared minus 1, so that derivative is 2x. So those cancel. And so another way of writing this would be x over the square root of x squared minus 1. So that's what I get for my function that was in the denominator. And that would be the same as limit as x approaches infinity. Dividing by a fraction is the same as multiplying by the reciprocal. Alright, so there we go. So this is our new problem. Wait a minute, that's just the reciprocal of the original. And we still get infinity over infinity. The L'Hopital to the rescue. Let's do it again. Do it again, do it again. Okay, the derivative of the function in the numerator. Well, we just got done doing that. That's going to be x over the square root of x squared minus 1. And then the derivative of the function in the denominator is 1. So it appears that we are back to the starting point. And unlike that integral problem with e to the x sine x, where it seemed like we were going in circles but really we weren't, we are definitely going in circles here. So that's not going to help. So L'Hopital is good, but not that good. So what are the other alternatives to solving a problem like this? Well, as I've talked about, you can try factoring, you can try multiplying by conjugates, you can try some algebraic manipulation. In this case, how about if we try to simplify or rewrite the denominator a little differently? So let's look at x over the square root of x squared minus 1. That's the same as, what if I factored an x squared out of the two terms inside the square root? I'd be left with 1 minus 1 over x squared. Don't believe me? Just redistribute that x squared. You'll see you wind up with what we started with. Okay. But now, what's the square root of x squared? I know what you're thinking. It's the absolute value of x. But since our limit is x is going to infinity, x is a positive number. So I don't have to worry about absolute value. So the square root of x squared is x. And I've got that. So now, what's the limit as x approaches infinity of 1 over the square root of 1 minus 1 over x squared? Well, now we can just go ahead and look at each of these parts individually. The limit as x goes to infinity of 1 is still 1. And the limit as x goes to infinity of 1 over x squared is 0, so we get the square root of 1 minus 0, or 1. So L'Hopital was not needed in the solving of this problem. Alright, let's see, how about this one? Limit as x goes to infinity of x squared over 2 to the x. Yeah, maybe give it a shot. I think you can probably see where this one's going to go. L'Hopital's rule does apply here. And because we get infinity over infinity, so we're going to take the derivatives. We'll get 2x Now, what's the derivative of 2 to the x? I forgot, that was a long time ago. Oh yeah, 2 to the x times ln of 2. ln of 2 is just a constant. Now let's take this limit. Oh, we still get infinity over infinity. So, L'Hopital, I call on you again. The derivative of the top is 2. The derivative of the bottom is 2 to the x ln of 2 times ln of 2, or ln of 2 squared. And now as x goes to infinity, the numerator stays at 2, but the denominator goes to 0. So we have, the denominator goes to infinity. So we have 2 over infinity, which is approaching 0. So as x gets really, really big, this fraction gets smaller and smaller and smaller, so it approaches 0. Alright, let's try one more. Alright, I'll let you go ahead and work this one out. Finished? Alright, let's check your work. So if I plug in, or if I take the derivative, as x goes to 0, derivative of the top is 1, derivative of the bottom is 1, so the limit as x approaches 0 is just 1. Did I catch you? Did I fool you? No, that's not the right answer, because L'Hopital's rule doesn't apply. What happens when you plug in 0 directly? 0 plus 42 is 42. 0 plus 1 is 1. The answer is 42. Just trying to see if you're still awake. Okay, so here's the assignment. It's out of the option book, Chapter 1, Section D, page 23. There's also an assignment set up in Schoology. So after you watch this, or if you just jump to the end to copy down the problems, work those out, and then please submit them as a PDF into Schoology when you finish. Hope that goes well. Hope you guys are doing well, and talk to you soon.